Hello, welcome to the project presentation of EEE426 Biomedical Signals, Instrumentation and Measurement Laboratory. I am Mose Rashid Suba from Group 5. The name of our project is Heart Abnormality Detection from Heart Sound Signals using MCC feature and dual stream attention-based network. This is the outline of our presentation for today. The heart sound signal carries early pathological information of cardiovascular disorders. It is also known as BCG signals and can be used to diagnose deformation in heart organs and damages to heart valves. The heart sound signal can be acquired from a patient using non-invasive, cost-effective methods, and it requires minimum equipment. But the detection of abnormality in heart sound depends heavily on the physician's clinical experience and expertise. As such, an automatic screening of heart sound signals with high accuracy has the potential to be a valuable early screening tool which can save lives. In this project, we propose a dual-stream attention-based deep neural network system to automatically perform binary classification of normal and abnormal heart sound signal using a large data set. The existing literature on this topic generally follows two kinds of approaches. One is using the raw data and the other is using the feature data. In the first approach, raw data is directly given as input to the model, which then performs the classification. In the second approach, the raw data is fed to a feature generator that generates different types of features. These features are given to the main model as input, and the classification is done based on these. Two references are included here for each of the approaches. I will now hand the presentation over to Shapnil Shaha. Thank you.
For our research task, we have used the Fusion and Computing in Cardiology Challenge 2016 public dataset. It consists about 3,000 recordings collected by 7 research groups from 7 countries. Among the recordings, 74% are normal and 26% are abnormal. For test split, we use 10% data for the test and 90% data for the training. To check the performance of the model correctly, we keep the equal ratio of normal and abnormal class in the test split. We detect 3 main challenges in the dataset. Throughout the presentation, we will show how we have overcome these challenges. To solve the presence of the various noise sources problem, we first analyze the noise data. We found 2 types of noise. One is the high spike amplitude and other is the non-relevant frequency component. To remove the high spike amplitude, we apply window method to detect and remove the global high spike amplitude. Then we made a bandpass filter to pass only the relevant frequency component. The main problem of this 1D dataset is that the recordings are not same in length. To solve this problem, we first segment the recordings into individual cycles. For example, in this recordings, there are 2 cycles. We extract these 2 cycles by segmentation. As the original recording is normal class, we label these 2 cycles as normal. Finally, we padded the cycle to a fixed length and make it suitable for the model input. To solve the third challenge, we oversample the abnormal class by 4 times. Now, as a result, in training, weights will be updated by observing equal number of normal and abnormal class in each batch. In our proposed methodology, we use the dual stream attention-based neural network to detect the abnormality. In first system, we use the raw signal passing through 1D CNN to generate the important feature. In next stream, we use MFC feature which pass through the GRU network. These 2 features are then combined using novel attention network and pass to the classification layer, which produce the final output. In data preprocessing block, we first sample the original data to 1000 Hz. Then we clean and segment it into cycles. Each cycles are then padded to 2.5 seconds, which is equivalent to 2500 sample length. These cycles are then fed to the model. Now, at this moment of the presentation, I'd like to overhand to the Naib Rashid.
Now, the preprocessed data is segmented and scaled and sent to the convolution stream of the proposed system. As convolution filters tend to learn better representation when the data is non-zero. The convolution network is made up of 6 convolution blocks and 4 max-pool layers that are each placed after a convolution block. Each convolution block consists of a 1D convolution layer, a batch normalization layer, and a leaky value activation function. The network is designed in such a way that as it gets deeper, the kernel size of the convolution block decreases while the number of filters increases. The output of the last pooling layer is flattened and passed to a dense layer of 64 units. In the recurrent stream, we first generate the MFCC features from the raw data, and these features are then flattened and passed through a GRU model. We tried other RNN models such as LSTM and transformers in place of GRU, but we got the best result using GRU model. The features generated from the GRU model are then passed to a dense layer of 64 length. Both the convolution stream and recurrent stream uses a dense layer of 64 units to convert their feature vectors to an equal length that is later used in the attention model. Now we merge the features of the 2 streams using an attention network. The equal sized feature vectors from both the streams are first concatenated. This concatenated feature vector of 128 length is then passed through a dense layer of 64 length and railway activation. By doing this, we downsample the feature, and it is then again upsampled to a length of 128 using another dense layer, which has a sigmoid activation function. Since this layer uses a sigmoid activation, it produces a probabilistic feature space that assigns a value close to 1 to the features that are more valuable in the classification task, and a value close to 0 to the features that has little impact to the classification task. This feature space is then multiplied with the concatenated feature vector. As a result, the concatenated feature vector now uses attention to strengthen the features that are more valuable for this task. It is then passed through 2 dense layers to make the final prediction. These are the experimental parameters that were used while training our deep learning model. We used a balanced batch sampler to tackle the problem of class imbalance in our dataset. Now I'll be handing over the presentation to Robin to talk us through the results section. Thank you.
Now, as previously stated, we first tested the audio cycles of our test set independently, and the audio cycles of a normal patient were all labeled as normal and vice versa. For this setup, we can see that the model has achieved an overall high accuracy of 84.16% and MSSC of 84.81% with good performance for both the cases. But ultimately, the system has to give prediction at patient level, so we average the results of all the audio cycles of a patient, and if the majority of the cycles were predicted as normal, then the patient was predicted to be normal, and vice versa for the abnormal case. This method further increases the performance of our proposed system. In this setup, we tested our fold 1 test dataset, and the model achieved a very high accuracy of 90.06% and predicted correctly for most of the patients of both class. We generated 4 random trained split of a dataset, and the model was trained and tested on all these 4 folds. We can see individual results of the folds in this table, and while the fold 2 performed poorly, the other folds gave somewhat consistent results. Taking the average of the results of these folds, we are presenting a more general and robust variation of our proposed system. Now, in the order to verify effectiveness of the previous models and techniques in our proposed system, we carried out an ablation study on the system. The results presented here are on the audio cycles levels of results of fold 1. As it can be seen, only the convolution stream achieves an accuracy of 81.81%, while the using only the recurrent stream gives an accuracy of only 57.71%. But when we use the MFCC features instead of the raw data on the recurrent stream, the accuracy jumps to 83.84%. Combining these 2 streams gives an accuracy of 83.84%, while combining them using the attention network gives our best accuracy of 84.16%. The results of the proposed systems are compared with the results of the existing literature methods that are also trained and tested on the same dataset. It can be seen that our model performs better than some methods, while its performance is very close to the others. So the proposed system is giving comparable results to the state-of-the-art methods. So now I am handing over this to Syed Murtaza Hassan for the rest of the presentation. Thank you.
One of the main challenges of this data set was the noisy signal that makes it difficult to differentiate between the normal and abnormal audio records. So a future direction of this research will be to develop a pre-processing model and unit loss functions by analyzing the characteristics of a noisy signal to produce noiseless signals that will be passed to the classification model. One other direction will be to use feature engineering in parallel to overcome shortage of peak values in the data. Estimated the cost of building this project in hardware, and it is going to cost around $425 for the data collection component and the prediction system in the hardware. That is all from us. Thank you. Please feel free to ask any questions.